has a certain similarity about it. And what is that question? Well, before we asked, it's the equality, like our two, before, when we're talking about two finite automata, I think D of A's? I think they're D of A's. So the question was, before, with two D of A's, A and B, do they recognize the same language? And a Turing machine that you can build a Turing, well, we proved it. You can construct a Turing machine that decides that question, yes or no, whether any two DFAs, deterministic finite automata, A and B, whether they recognize the same language or not. Okay. All right. Well, by analogy now, we're going to do something similar. Ask the same question. Instead of being given now two machines, two DFAs, we're now given two grammars, two context-free grammars, okay, A and B, or G1 and G2, if you like, or G and H, right? Okay. So you're given any two context-free grammars, CFGs, okay? Grammar 1, so G, and grammar 2, H. And the question is, are these two languages, remember a language, when you're talking about a grammar, a language is the set of all strings that grammar generates. Right? That's the definition of L of the grammar, L of LG, L of H. And the Turing machine is to determine, yes or no, whether the language generated by G is equal to the language generated by H. But are the two languages generated by these two grammars, G and H, or G1, G2, are they the same or not? Are they equal? Right? These two sets, I mean, language is the set of strings, so is this set equal to that set? That's the question. That's so you're trying to find an algorithm, Turing machine, that will answer that question. Right? Will decide that set, the language. So let's create the language. Now it's a similar trick as we've been doing consistently. So we reformulate the problem in form of a language, and membership or non-membership of a language. And so the strings in this language is a set of strings. So the strings in this language, you have an encoding, a string encoding of the details of form a definition if you like, of two grammars, right? All the substitution rules, the set of terminals, the set of variables, blah blah blah. All the details you need about these two grammars, context-free grammars, G and H. Okay, so all that information goes into the Turing machine, and the Turing machine is to decide. In other words, it will accept this string if, well, what's the condition that this ordered pair, this string, is in the set of this language? Language is just a set. Right? So what's the property that the element of the set must have to be an element of the set? Well, it's here. Well, the two conditions. G and H are context-free grammars, and the other condition, property it must have, is that the language of G is the same as the language of H. Okay, so imagine this Turing machine can be found, constructed. Right? It would be a proof by construction if it can be done. So imagine this machine is built, and then it would then have as input any two context-free grammars, G and H, and it would decide. Would make a decision, yes or no, accept or reject, that these two grammars generate the same language. Right? Okay. Now, again by analogy, if you go back to Theorem 4.5, that was on page 171 of your text, and same comment as before. Theorem numbers don't mean anything, and page numbers don't mean anything. So. I need to refresh what that was about. So page 171, theorem 4.5. That language was EQ and suffix DFA. In other words, the theorem was about finding a Turing machine that could decide, yes or no, accept or reject, whether two DFAs, two machines, two finite automata, or DFAs, recognize the same language. Okay, and we did that. If you remember, remember the previous board. Something called the symmetric difference of the two languages. So L of, well, you've got two DFAs, A and B. So you may think, well, and we used this, well, here it is here. So this language, EQ DFA, that was our test, whether two DFAs have the same, recognize the same language. Now, how about by analogy? We've just done, previous theorem, we've just done ECFG, which is analogous to EDFA. Okay. Now, we know this is decidable, right? There's we can find a Turing machine that gives a decision, yes or no, accept or reject, for that problem. We also know, because these are two separate theorems, we know there's a Turing machine, an algorithm that accepts this one, whether two DFAs, finite automata, are equal or not. Right? So decidable, both these languages. And we've just proved previous theorem. We've just proved that that's decidable. Okay. So how about this one? So could we prove this one in the same kind of way that we proved this one? In other words, use this somehow with the analogous symmetric difference property. Now the languages this time, they wouldn't be languages recognized by automata, by DFAs. They would be obviously languages generated by the grammars, the two grammars. Okay, but they're still just languages, right? So how about using the symmetric difference idea that you used for proving this one? How about using that same idea for proving this one? Okay, that's the idea. And I hope you follow that. So if you're a bit rusty, go back to how you proved this one. I think that's theorem 4.5. Yeah, EQ subscript DFA is decidable. That's on page 171. Okay, so that's the idea. So use a symmetric difference strategy using this that we've just proved, that's the previous theorem, and see if we can prove this, right? But there's a catch, there's something wrong with this idea. And that is to prove this,